Hello, my name is Martin Dernay. I am a PhD student at the German Research Institute for Cyber Defense. Today, I want to tell you about a project I've been working on with my supervisor, Stefan Bruntaler, that aims to bring us toward efficient and verified virtual machines for dynamic languages. Those days, dynamic languages can be found everywhere. The most obvious example is the web, where JavaScript programs are automatically downloaded and executed by your web browser. But it is also very common to use them on mobile devices, on servers, in video games, etc. In most cases, programs written in such languages are either shipped directly as source code or in an intermediate language called bytecode. A bytecode language is an efficient machine-readable encoding for a sequence of instructions that have a level of abstraction somewhere between the original programming language and machine-native assembly. Each time the program is executed, it is fed to a virtual machine which first compiles it on the fly to bytecode if it's not already done, and second, executes the resulting program by interpreting each instruction one after the other. At its root, this execution model is very simple and convenient, as it allows to distribute only one version of programs and execute it on a variety of different environments, as long, that is, as a compatible virtual machine is available. But the shortcoming is that the execution of these programs tends to be much slower than that of native program produced by optimizing ahead-of-time compilers. To reduce this performance gap, virtual machines employ a variety of techniques to optimize their programs at runtime. To this day, the most successful optimization was the introduction of just-in-time compilers. In a nutshell, the bytecode is compiled at runtime to input specific machine-native code, so that if a program is given input in a certain range, the generated machine code will be specialized for this input pattern. If, at another point in the future, a new input pattern emerges, the machine code is thrown away and the bytecode is recompiled. Thanks to just-in-time compilers, virtual machines can achieve near-C performance. But in this quest for performance, industrial-strength virtual compilers have evolved into massive and complex programs whose code base now contain millions of lines of code. This increase in complexity came at a very high cost in correctness and security, as new bugs and vulnerabilities are regularly discovered. Could formal methods help improve the situation? Could we apply the ComSort technique and formally verify the correctness of a just-in-time compiler? We are rather skeptical about that. You see, compilers are relatively simple programs that perform their task by moving data through a pipeline. Virtual machines, with just-in-time compilers, on the other hand, are complex, possibly non-terminating programs that manipulate an ever-changing state. It would be more accurate to compare them to hardware processors. But also not entirely. The other problem is that virtual machines constantly modify their own program at runtime when just-in-time compiling new specialized versions of functions. It is not entirely clear how to formally reason about such self-modifying programs. And worst, even if we were to fully formalize such a virtual machine and exclude all possible bugs, the mere nature of dynamic code generation is a security liability. You see, the first step of most attacks is to get the processor of the victim system to execute some code under the control of the attacker. Since compilers are more or less deterministic translators, every single function that gets just-in-time compiled could be the payload of such an attack. We believe that, instead of trying to verify complex just-in-time compilers, we should try to apply simple optimizations to verified bytecode interpreters. Remember that, at their core, virtual machines are relatively simple programs, and that means that they could realistically be fully formalized. The main problem is their performance. But not all programs need to run at extreme speed. There is such a thing as good enough performance. We aim to find a balance between complexity of the virtual machine and its performance, thus increasing the number of programs hitting this sweet spot with good enough performance. We aim to achieve that through few, simple optimizations that do not require dynamic code generation. This belief in this method is strengthened by premising experience from my co-author with an early Python implementation a few years ago. He then noticed that such simple optimization can bring us a good step forward in the direction of just-in-time compilers' performance. So based on those premises, we specified 3 bytecode languages that incrementally support more optimizations. DIN is the baseline that we extend with speculative optimizations, with a speculative optimization called inline caching to form Inca. We then extend it again with unboxing to form MuBX. For each language, we define a realistic small-step operational semantics, a simple optimizing compiler, and a bisimulation relation that ensures that executing a compiled program exhibits the same behavior as executing the original program. We mechanized our formalization in Isabelle Hall and ended up with a total of around 5,800 lines. We made extensive use of Isabelle's locales to abstract over implementation details not relevant for the optimizations. As an example, when defining the bisimulation between Inca and MuBX, we use 11 abstract types, 28 abstract functions, and an appreciable number of assumptions on the meaning of those functions. As a sanity check, we provided concrete instantiations for all the abstracted details to rule out any unsoundness in the assumptions. So let's start with DIN, which is a simple stack-based interpreter for dynamically typed language. It supports the most representative features of mainstream bytecode languages. It has instructions to manipulate the operand stack, load values from dynamic memory, and store them back. It supports an arbitrary number of n-ary operations, which could be anything from basic arithmetic to string manipulation, or really anything that a concrete implementation wants to natively support. For control flow, there is support for conditional jumps, function calls, and arbitrary recursion. But really the key concept of such dynamic languages is that of the manipulated values. All supported data types are gathered in a tagged union of dynamic values. There is one tag, also known as a constructor, for each primitive type. The different instructions and operations all manipulate values of the dynamic data type and perform type checks at runtime before extracting the native value. In the following examples, we are going to concentrate on the 2 cases of the DI constructor, which holds an integer, and the df constructor, which holds a floating point number. To get a better understanding, let us consider the execution of this small example program that performs a conversion of Fahrenheit to Celsius. At the beginning, the operand stack is empty. When the virtual machine executes the load instruction, it fetches the number 65 from dynamic memory and pushes it onto the stack. Notice the constructor keeping track that it is a floating point number. The next instruction pushes the integer 32. Here, we see that it is an integer. And the next is a subtraction operation that pops the 2 topmost operands and pushes the difference. Notice that the difference is also a floating point number. The execution continues until the final result remains on the stack, at which point the store instruction saves it into dynamic memory. Now, because of the dynamic nature of the operand, the same program could have different behavior depending on the input value. Let's consider the case where the same Fahrenheit value is represented not as a floating point number, but as an integer. Again, the number 65 is loaded from memory and pushed onto the stack. This time, the constructor indicates that it is an integer. The execution continues up to the final division, but then in this case, an integer division is used in such a way that the quotient is truncated, resulting in 18 being stored to memory instead of 18 as previously. This emphasizes the fact that an operation's behavior depends on the dynamic type of its operands. This is implemented in a fashion akin to the following, which uses an ML-like syntax for illustration purpose. When the virtual machine encounters an operation instruction, it calls an eval function with the specified operation and the arguments taken from the operand stacks. The eval function starts with a pattern matching on the operation, div in this example, and continues with a linear comparison of the arguments types with the types required by each possible implementation until at one point a matching implementation is found to calculate the result. In this example, with a float as an integer as argument, the 6 type checks were required. In comparison, evaluating a division of 2 integers would only require 2 type checks, because this is the first potential implementation that is tested on the first line. This implies that our Fahrenheit to Celsius converter will systematically be a little bit slower for floating point numbers than for integers. If this conversion is performed many times, for example in a loop, this difference in performance can noticeably impact the performance of the full program. So sure, we could put the implementation for float and integer on the first line, but that would only move the problem somewhere else, because it would then be the implementation of for 2 integers that would have suboptimal performance. The inlining optimization tries to solve this problem by providing multiple versions of the division operation. Each of those versions puts a different type combination on the first line. So when evaluating this inline operation, only 2 type checks are required. It is then the job of the virtual machine to try to keep track of the best fitting version to minimize the number of type checks. But even if the virtual machine was to make a mistake and use a suboptimal inline operation, this mistake wouldn't be that bad, because evaluating the wrong inline version would simply perform more type checks before finding the passing implementation, and the correct result would still be computed. So we have 2 disjoint sets of operation. The left one, up, contains the original operations, and the right one, up inline, contains a certain number of inline versions. The solid arrow is a function which maps an operation to the inline operation best fitting some concrete arguments encountered by the virtual machine, if any exist. Formally, we use the locale to abstract over the set of operations and their implementations. Locales are Isabelle's way of expressing an interface akin to a ML functor or a coq-dependent record. All blue types are abstract types, and the fixed keyword introduces a list of abstract function declarations. This is where we find for the eval function whose implementation we just looked at. A second locale introduces the abstract set of inline operations, the evaluation function, the mapping from one set to the other, and its inverse. Finally, we state a number of assumptions that these abstract operations must fulfill. For example, we state that an inline operation must evaluate to the exact same value as the non-inline version, and also that the inlining process is invertible. Equipped with all of that, we extend the DIN bytecode language with inline caching to form the Inca language. We introduce one new instruction for inline operations and update the semantics accordingly. The rule evaluating operations is expanded to cover 2 cases. If there exists an inline variant of the operation being executed, the program is rewritten to subsequently use it. Otherwise, execution continues as previously. We also add 2 rules for the new instruction for inline operations. When an inline operation is evaluated on arguments of the expected types, we call that a cache hit, and we know that we got the best possible performance. Otherwise, we call that a cache miss, and we cannot make any statement on the performance of this operation. So we revert back the program to use the original non-inline operation so that it can be get optimized again on the next execution. Let's get back to our Fahrenheit to Celsius converter and look at its execution as an Inca program. The table at the bottom left compares the number of type checks required in the DIN and Inca virtual machines respectively. The execution starts as previously. When it encounters an operation instruction, the virtual machine searches for an inline version for float and int. It finds one, evaluates it on the arguments, and rewrites the program to remember this optimization. Here, Inca requires slightly more type checks than DIN because the former performs a slow search plus a fast evaluation, while the latter only performs a slow evaluation. The execution continues and some more operations get inlined. On the first pass, we see that that Inca was slower than DIN because it had to pay the upfront cost of optimizing the program. But on subsequent passes, in case of a cache hit, the inline operations are directly used and the Inca virtual machine needs less type check in total and will perform better. This kind of speculative optimization takes a gamble on the fact that successive execution of the program will have input of the same type. This heuristic is based on the empirical observation that dynamic programs tend to stick to one dynamic type for most of their execution. So, how do we compile a DIN program to an Inca program? Well, because the full optimization is performed at runtime, the compiler only has to trivially lift the instructions of all function definitions. So then, to prove the soundness of this optimization, we prove that there exists a bisimulation between a program and its compiled version. Completeness, on the other hand, can be reduced to the fact that the compiler is a total function. Now, while inlining can reduce the number of type checks necessary to evaluate an operation, there is still some remaining overhead. The type of each argument needs to be checked. The machine native value has to be extracted from the dynamic constructor, and a dynamic value has to be allocated to hold the result. This is suboptimal in multiple ways. First, even in the case of a cache hit, one type check per argument is required. And second, the dynamic values are usually allocated in dynamic memory and the operand stack only manipulates pointers to them. This implies that operations must dereference the pointers of all their arguments to get access to the tag and the native values. If the dynamic value is in a CPU cache line, that's not that bad, but it often has to be fetched from the RAM, which could be much slower than performing the division itself. Finally, the memory allocation for the result is also usually a slow operation that also adds stress to the garbage collector. The unboxing optimization tries to avoid these problems by bypassing the dynamic constructors, which we call boxes, and whenever possible, working directly with the machine native values, which we then call unboxed. The operand stack is adapted to manipulate a mix of boxed and unboxed values and to pass to cast the appropriate to the appropriate types for the operations. In this example, the division has direct access to the argument x of type float and y of type int. It needs neither to dereference pointers, nor check their type, nor allocate memory to hold the result. It directly performs the appropriate conversion and division and returns its result. All of that probably taking place only in the fast CPU registers without ever touching neither the cache and CPU cache lines nor the RAM. The flip side of this optimization is that this unboxed division now only makes sense for floating point numbers and integers. Passing it boxed values or unboxed values of the wrong type, such as a boolean or a string, would result in complete garbage being computed. The virtual machine must thus ensure that all instructions get fed the operand of the expected types. This is what the UBX bytecode language does. It extends Inca with instructions to push unboxed contents on the stack, load unboxed values from dynamic memory, and store them back, and evaluates unboxed operations. The operand stack is changed to manage a union of boxed and unboxed values. For this to work, all semantics rules from Inca have to be adapted to cast the operands to the correct types. But then the question is how we can be sure that the operands have the correct types and that this casting is sound. The unboxed operations must be the unboxed operations must be strategically placed so that loading a value of the correct type will start an avalanche effect of correct casts. If the loaded value does not have the expected type, then the unboxing cannot work and must be undone so that the boxed versions of the operations can take care of this unexpected type. Let's see what this looks like for our Fahrenheit to Celsius converter. This optimized version of the program expects to load a floating point number from memory. When executing the load instruction, the dynamic value has the expected type and represents a cache hit. The machine native number 65 is unboxed and pushed onto the stack. That is, without a def constructor. The next instruction pushes an integer. Now, the subtraction instruction casts the two uppermost operands of the to the expected float and int types and performs its calculation. It then pushes its unboxed result back. Execution continues until the last instruction boxes the final result to a float and stores it into memory, where the def constructor boxes it. So that was the ideal case of a cache hit, but what would happen if we had a cache miss? For example, if the Fahrenheit value was an integer and not a floating point number. In this case, the load instruction notices the type mismatch and needs to undo the optimization. All the instructions that transitively depend on this operand needed to be reverted back to Inca instructions so that they can operate on dynamic values. The box number is pushed onto the stack, again with the di constructor. And then the execution continues exactly as in the Inca case until the final result is computed and stored into memory. This execution was slower than hoped, but it is guaranteed to still compute the correct value. So the remaining question is how to optimize a program to take advantage of this unboxing. For that, we use a static optimization path that performs an abstract interpretation, computes the types of the operand that will be placed on the stack at runtime, and replace the instructions with an unboxed variant whenever possible. Some type information on the operands can be extracted statically from the programs by code itself. For example, the exact type of constants is always known, and we specified that function parameters and results have to always be boxed values. Some other information is the result of the static analysis performed by the abstract interpretation. The one case where the information is not available is when loading values from memory. In this case, we ask an oracle that what the expected type is. In the formalization, we modeled this oracle as an abstract function. In practice, there are two general principles on how to get this information. We could, on one side, ask the programmer to give us an optimization hint through either a pragma in the source code or some execution option when running the virtual machine or anything of the like. The other possibility, which is usually used, is that the virtual machine runs for some time without the optimization and gathers some statistics on the encountered types. When the instrumentation indicates that the type usage has stabilized, the optimization is performed, and then the virtual machine continues execution with the unboxed version. This looks a little bit like that. When the abstract interpretation reaches a load instruction, it asks the oracle what the expected type of the Fahrenheit variable is. The oracle answers that a float is expected. The load instruction is rewritten to unbox the float, and the type information is pushed onto the stack. Constant can always be trivially optimized. And now, because the type information is available on the stack, then when an operation is encountered, we can just check that if this type information in the stack corresponds to the types expected by the operand. If it is the case, the operation can be unboxed. The abstract interpretation continues and optimizes as many instructions as possible until, when a stored instruction is encountered, it is rewritten to box the result found on the stack. In the formalization, we define the compiler as a function that lifts instructions from Inca to UBX, then performs a single pass optimizing abstract interpretation, and finally inspect the output of the optimization pass and uses it if it is any good, or falls back to the unoptimized version otherwise. The compilation is sound, as in, if it succeeds, then there exists a bisimulation between the program and its compiled version. This bisimulation ensures that at every step of the execution, the type of the operands on the operand stack correspond to the result of the abstract interpretation. This implies that compilation can only succeed for sensible programs, by which we imply that all instructions are fed the correct number of operands. Otherwise, the abstract interpretation would fail, and it would not be possible to fulfill the requirement of the bisimulation. It should be possible to check that programs are sensible with a minimal type system that only keeps tracks of the arity of the instructions. If such a type system was in place, we could say that the compiler is complete for all well-typed programs. So in summary, we covered 3 bytecode languages that implement 2 speculative optimizations. DIN is our baseline. Inca implements inline caching, which replaces operations to minimize the number of type checks. And UBX implements unboxing, which replaces as many instructions as possible and changes the data representation to reduce the number of type checks even further, the number of heap allocations, and also the number of pointer dereferencing. Our formalization was mechanized in Isabelle, where we specified a realistic small-step operational semantics for all of these 3 languages, while still trying to keep multiple details abstract through Isabelle's local mechanism. The formalization will be available under this URL in the next version of the archive of formal proofs, which should be released in a few weeks from now. For the impatient, there is a direct link to the development version in the paper. So, thank you for your attention and have a nice day.